Welcome back to this next video in which we are discussing p-groups. Okay, so in this next video what we're going to have a look at is another theorem concerning p-groups. Okay, and we'll call this theorem, continuing with the pattern, Theorem 4. Okay, so Theorem 4 is going to concern subgroups of your p-group. So once again, we'll denote by capital P our p-group. Okay, so capital P will be our p-group and it will have order p to the power of some a, okay, and Theorem 4 is going to, as I say, concern subgroups of this. So let's say now that we have capital H, which is a proper subgroup of capital P. So I'm only interested in proper subgroups, okay, so I don't want the improper subgroup. You can have the trivial subgroup because that's still a proper subgroup, but we're only interested in proper subgroups, not the improper subgroup. Okay, then Theorem 4 says that capital H will be properly contained in its normalizer within the p group capital P. So the normalizer of capital H in capital P will properly contain capital H. Now let me just explain this in a little bit more detail. So let's remind ourselves, of the definition for the normalizer of a subgroup capital H in a group capital P. Okay, so remember this is the subset of the group capital P of elements which, if you use them to conjugate capital H, fix capital H. So this is all little g is an element of capital P, such that if I use little g to conjugate capital H, so if I take GH, G inverse, the answer, the subgroup that I get back, is the same subgroup as I started off with. And remember, what I'll have to do is go through and conjugate every element of the subgroup capital H, collect all of the answers together. You're guaranteed to end up with a subgroup of capital P back again, but I want the elements which, if you use them to conjugate capital H, give you capital H back again. The elements which normalize capital H. Okay, right, so this subcollection of elements of capital P, this is what's known as the normalizer of capital H in P. Now, of course, capital H, all of the elements of capital H itself will always be contained within its normalizer. Okay, that's not the interesting fact here, okay, because capital H is a group in its own right after all, and we know that whenever we use an element of a group to conjugate the entire group, you get that entire group back again. Okay, conjugation by an element is an inner automorphism, remember. Okay, so it is a bijective map from the group onto itself. So the interesting thing isn't that H is contained within its normalizer. The interesting thing is that this containment is proper containment. Okay, so there are elements outside of capital H, but which are inside of capital P, which when they are used to conjugate capital H, will give you capital H back again. Always, if we're working inside a p group. That is what Theorem 4 is about. Okay, so to overall now state Theorem 4, Theorem 4 is that if you have a proper subgroup of your p group, then there will exist an element outside of capital H, inside of capital P, which if you use it to conjugate capital H, will normalize capital H and will give you capital H as the answer. Okay, right. So let's turn our attention to the proof of this, and we're going to do another proof by induction. Okay, so it's a nice video for practicing proof by induction. Okay, so again we will be inducting on the value of a here. Okay, so our arguments will work for a general little p, and that's why we'll end up proving this for all possible p groups. Okay, so we won't specify p at all, it'll be a general prime natural number, and the arguments will work for all of them, and hence, if we can prove it for all a for each of the prime numbers, then we will have proven it for all p groups. Okay, so let's start off with the basic one, where a is equal to 1. Okay, in that case, our p group has order just equal to a prime number. Okay, well I hope you agree that it's trivially obvious then that Theorem 4 will be true, and the reason is that if your p group has order just equal to a prime number, then we know that any group of order a prime number by Lagrange's theorem has only two subgroups, the trivial and improper subgroup. So that doesn't leave us with many options as to what capital H we need to check that this theorem is going to be true for. The only one is going to be the trivial subgroup, and of course the trivial subgroup is normalized by all the elements of the group capital P. Okay, if you conjugate the identity element by any element of a group, you will just get the identity element back again. So indeed, the trivial subgroup is always a normal subgroup. Okay, so indeed the trivial subgroup will properly be contained in its normalizer because its normalizer will equal the entire group. So it's obvious when A is equal to 1. We will now do the inductive assumption, so we will assume that it is true for, let's say, A is less than K. Okay, and of course what we then need to do is prove that if that's the case, it will also be true for the next one along where A is equal to K. And of course if we can do this, then because it's true for A is equal to 1, it will imply that it is true for A is equal to 2, and because it's true for A is equal to 1 and 2, it will imply it's true for A is equal to 3, etc. And it will therefore apply for all powers of P, and since we're keeping P general, it will apply for all P groups. So that's going to be our tactics. Okay, so now what we are left with trying to do is using the fact that this theorem is true when A is less than K to prove that the theorem is going to be true where we have our P group of order P to the power of K here. Okay, so this is what we now want to do. We want to prove that it is the case that if you've got a subgroup of this P group here, that it's going to be properly contained within its own normalizer, i.e. that there is going to be an element outside of it which normalizes it. Okay, so let's take our subgroup. So let's just say H, capital H here, is some proper subgroup of capital P. Okay, from here on in, what we're going to do is split it into two different cases. So case 1 and case 2. Okay, so case 1 is the case where there are elements of the centre of the group, the centre of the P group, that are not in capital H. Okay, and you will understand why that has anything to do with the question we're trying to answer in just a moment. Okay, so case 1 is where if you intersect the centre of the P group with H, you do not get the entire centre as your answer. Okay, so remember the centre of the group is this subgroup of P that contains all the elements which will commute with all other elements of the P group. Okay? Now, what I'm saying is we are now saying that not all of the elements at the centre of P, well, firstly we know from theorem 1 that the centre of P is not just the trivial subgroup. Okay, it contains more elements than just the trivial subgroup. Now, why is the centre of P relevant to us when we're trying to show that there are elements in capital P that will normalize capital H that are outside of capital H? Well, my claim is that all the elements at the centre of P are going to normalize capital H. So if you use an element, let's say little g, from the centre of the P group to conjugate capital H, okay, you will always get capital H back again, because this element, little g here, this commutes with all the other elements of the group. So when you're going through the elements of this subgroup, capital H, and conjugating each of them by g, it's not going to change that element at all, because you can just swap, let's say, g and the element in the middle around, and then the g and g inverse can cancel, so it'll just map any element of this subgroup onto itself. So indeed, when you conjugate the entire subgroup by any element of the centre, of course it fixes it. Okay, so if it's the case then that not all the elements of the centre are in capital H, i.e. if you intersect them two together you do not get the entire centre back again, then those elements of the centre are going to be in the normalizer of H and P, as I've shown you here. So you'd have an element in the normalizer of H and P that was not in capital H, and you'd be done. Okay, so case 1 is the easy case. If there are elements of the centre of the P group, which we know is not the trivial subgroup, that are not in your subgroup capital H, then instantly you can say, okay, those elements are going to be in the normalizer of H and P, and therefore I found you an element that's outside of capital H that is in the normalizer of H and P, so we can conclude that H is going to be a proper subgroup of the normalizer of H and P. Done. Okay, so that's the easy case. The other case is that all the elements of the centre of P are in capital H. So that's more difficult. So that's the case where H intersect the centre of P is equal to the entire centre of P. Okay, that's more difficult because the centre of P was like our instant go-to for elements which would normalise capital H. But now we're saying that all of those are in capital H, so we can't use those as examples of elements that are outside of capital H, which if we use them to conjugate capital H will give capital H back again. Okay, so what are we going to do now? This is the more difficult case. Okay, well what we can say is if this is the case, then the centre of P is going to be a subgroup of capital H, which of course is then a subgroup, a proper subgroup of capital P. I was about to write capital G, then I remembered capital P here. Okay, right. So, what is this crying out for us to do? Well, this is crying out for us to employ the same tactic as we used in the previous proof by induction. We need to somehow use the inductive assumption, but to do the inductive assumption we need a P group which is order a lower power of P than P to the power of K. So let's form a quotient group, and the sort of obvious thing to do is to quotient P out by the centre of P, which I'll give you an argument in a moment as to why that's a normal subgroup always, because then look, H is between these two, so by the correspondence theorem it will then have a corresponding subgroup in the quotient group, and we might be able to go somewhere with that. Okay, and indeed we will be able to. So let me firstly just show you the setup for this. So we're going to quotient P out by its centre. Okay, the centre of P will always be a normal subgroup in capital P. The reason being that if you take any element from capital P, so for all little g in capital P, if you use that to conjugate the centre, okay, which means go through all of the elements at the centre and conjugate each one of them by this element little g, then of course because all the elements at the centre commute with little g, you can just swap, well, commute with any element of the group, you can just swap it around with little g. The little g can cancel with the little g inverse and it will just map it onto itself. So indeed every element will be fixed and therefore you will get the entire subgroup back again. Okay, so the centre of the group will always be a normal subgroup of capital P. Okay, so we can indeed quotient the group capital P out by its centre. Now let's think about what the order of this is going to be. Remember, the centre of the P group is not the trivial subgroup. Okay, now by Lagrange's theorem, its order must divide the order of the group, so it must be some power of P. Okay, so when we ask about the order of the quotient group here, it's going to be the order of capital P, which is P to the K here, divided by some power of P. Okay, so this is going to be P to the power of J, and the key thing here is that J is less than K. I can't say exactly what it is because I don't know what the size of the centre of P exactly is, but what I can say is it is not P to the K. It's strictly less than P to the K, okay, because the centre of P is not the trivial subgroup here. Okay, so we are performing an interesting quotient here. Okay, right, so we quotient our P group, capital P, out by its centre, and we end up with another smaller P group. Okay, now by the correspondence theorem, capital H, because it completely contains the centre of P, it's going to have a corresponding subgroup, which I will call H bar. Okay, so everything to do with the quotient group, I'll bar. Okay, so it will have a corresponding subgroup H bar, which will be a proper subgroup now in the quotient group, P quotiented out by the centre of P. The reason it will be proper is that it was a proper subgroup of P. Okay, so drawing a picture for this then, okay, so let's have the entire group capital P shown by this box here, and I'll just colour this in red like so, and then we'll have the centre of the P group shown on here, and then of course it will be dividing P up into its cosets. So I'll show this like so. So we'll have 8 cosets, which is my favourite number to show. Okay, 1, 2, 3, 4, 5, 6, and then 7 and 8. And then we'll have the centre of P over here, which I'll colour in orange like so. So here's the centre of P, and we've quotiented P up into these cosets, which are the elements then of the quotient group that we've got over here. Now, capital H then, to put capital H on here, it was a proper subgroup of P that contains the centre of P. So how can we have capital H shown on here? Okay, well, I'll outline it in green here. So let's say here it is. It contains the centre of P here, like so. And let's say it was slightly bigger than the centre of P. Of course, it could have been equal to the centre of P, but more generally, let's say it's bigger than the centre of P, as indeed I've shown on this picture here. The point is that it is now going to correspond to a subgroup of the quotient group here, which is the subgroup that you would get by just quotienting it up into its cosets according to the centre. So this would be H quotiented out by the centre of P. H bar would be H quotiented out by the centre of P. Here it would consist of just two elements, this coset here, the identity coset, and another coset there. Okay, so this is the normal way that the correspondence theorem works. If you've got a subgroup that is in between the thing that you're quotienting out with and the thing that you're quotienting out, then you can just quotient this subgroup out by the normal subgroup, because of course this will still be normal inside a subgroup of this, okay, and that set of cosets you get, that will be a subgroup of the quotient group. Okay, so we can find then this corresponding subgroup of the quotient group H bar here, which corresponds to our subgroup capital H. And now, of course, what we can do is apply the inductive assumption. This quotient group is a P group of power of P less than K. So what we can now say is, look, I've got this proper subgroup of the quotient group, therefore it's going to be completely contained in its normalizer in here. Okay, so it will be properly contained within the normalizer of itself in the quotient group, which I'll call P bar. Okay, so let's rename the quotient group. So P bar is my shorthand name for P quotiented out by the centre of P. The normalizer of H bar in P bar. Okay, so you could work this out. The quotient group is a group. You've got this subgroup of inside the quotient group. You could work out what the normalizer of that subgroup inside the quotient group was, and by the inductive assumption it's going to properly contain the initial subgroup because the quotient group is still a P group. Okay, right, so drawing this on this picture, maybe the normalizer of H bar in P bar might look something like this. Okay, so I'll outline it in purple here. Okay, so here it is. It consists of these four cosets here, and you can see that it contains H bar, which is just these two cosets here. Okay, so let's just add that onto the picture. So this is the normalizer of H bar in P bar here, and I'll underline it in purple. Okay, now the thing is that normalizers like this correspond across, correspond as well according to the correspondence theorem. Okay, so if we were to go back to our original setup here, where we just had H, which was in between the centre of P and P, we could construct the normalizer of H in P, of course. Okay, and what we're trying to prove is that this properly contains capital H. And the way that I can prove it is because if I was to take this subgroup here, which would have to contain capital H and therefore would contain the centre of P, and therefore is a subgroup in between these two, if I was to take this and find its corresponding subgroup of the quotient group, then it would be this. Okay, so if you like, the normalizer of H in P bar the subgroup of the quotient group that this subgroup that's in between the centre of P and P would correspond to is this. Normalizers correspond, and let me just give you the argument as to why that is. Okay, so the reason that normalizers have to correspond in this way is, if you think about this one, we know that the normalizer will contain capital H, always. Okay, so H will be a normal subgroup in the normalizer of H in P. We also know that the normalizer of H in P is going to be a subgroup of capital P. Okay, we also know that H completely contains the centre of P, and therefore that this is one of these subgroups in between the two. Okay, so we could take the thing that it corresponds to. Now, look, it normally contains capital H. H is normal inside this. So the thing that this would correspond to, the normalizer of H in P bar, the subgroup of the quotient group that this corresponds to, the normalizer of H in P corresponds to, this would have to normally contain H bar. So H bar would have to be normal a normal subgroup of the normalizer of H in P bar. Okay, so what that tells us is that this would have to be contained in the normalizer of H bar in P bar. So this itself would have to be a subgroup of the normalizer of H bar in P bar, because remember, the normalizer of H bar in P bar is the largest subgroup of the quotient group P bar in which H bar is normal. Now, because, as I say, normality transfers in the correspondence theorem, when I take the normalizer of H in P, which contains H normally, and transfer it across here, which I can do just by the normal correspondence theorem, okay, and get the normalizer of H in P bar, okay, this will still normally contain H bar, which is the corresponding thing for H. Okay, so that's because normality transfers across when we apply the correspondence theorem. That's proved in the video on the third isomorphism theorem. So what I can now conclude is that this normalizer of H in P bar, which is this thing transferred across, must be contained within the normalizer of H bar in P bar, which is the normalizer of H bar in P bar, of course. Okay, right, but now I can prove that this has to be, these two have to be equal to one another, because what I can now do is say, okay, on this side, we have that H bar is going to be a normal subgroup inside of its normalizer, so inside of the normalizer of H bar in P bar. What we can then do is, because this is a subgroup of the quotient group, we can then take it back, basically. We can take it back into being a subgroup of P that contains the centre of P, and it will end up containing H, of course. So we can take it back onto the other side, and this then will end up being a subgroup of P that will normally contain capital H, again because normality has to transfer. Okay, so it's transferred would end up having to be contained in the normalizer of H in P, which is the smallest subgroup of P that, the largest subgroup of P that contains all of the elements which normalize H. Okay, so it would end up, once being transferred, having to be a subgroup of that. But this can't be a subgroup of this when it's transferred, and this being a subgroup of this one when it's transferred, so they then have to be equal to one another, otherwise you'd arrive at a contradiction. Okay, so this is why you can conclude that these normalizers do correspond to one another. So the normalizer of H in P is going to correspond to the normalizer of H bar in P bar, and vice versa. You can go either way between the two of these. Okay, right. So now what we're able to conclude is, because of the inductive assumption, we were able to conclude that H bar was properly contained in the normalizer of H bar and P bar, and what we can now do is go back, take this backwards to the normalizer of H in P, and we can conclude that H must be properly contained within the normalizer of H in P. Okay, so H is indeed going to be a proper normal subgroup of the normalizer of H in P. Again, that is why we can do this. So we have now proven that indeed the theorem will be true for the order of P is equal to P to the K, provided that it was true for A is less than K, so for a group of order P to the power of A where A was less than K. Okay, and since it's true for A is equal to 1, it will then be true for A is equal to 2, and A is equal to 3, A is equal to 4, etc. Okay, so there's the proof of theorem 4. Again, we'll have a break here and then we'll prove the final theorem for this video, and then we'll be done.